Hi, I'm Addison. Today we are going to do some work writing code using the 32-byte YMM registers. To use this instruction set, you will need to have an Intel CPU that is generation 4 or later and what is called the Haswell instruction set. For AMD CPUs you will need to check your reference material, but if you have a processor that is less than 6 to 7 years old, it will probably handle YMM registers. What I am setting out to do is show you how to set up a properly aligned procedure, where you can perform YMM operations using the fastest aligned instructions, and use properly aligned local variables that are safe to use with the faster aligned instructions. The stack frame is different to the normal one, as it needs to be aligned to work with YMM registers. The YMM stack has recently been updated to ensure it works correctly with YMM registers. Make sure you get the updated version of the 64-bit YMM macro file, as it also contains a specialized macro for testing stack frame alignment. To use aligned YMM instructions, you must use correctly aligned memory, which in this case is 32-byte alignment. The example is set up much the same way as the one done by Billy in a previous video. There are two local variables, a pointer to allocated memory, and another pointer to an aligned location within that memory. A buffer size for the allocation is set in this example as an equate to keep the code more compact. After any runtime code has been executed, the procedure caller must free the memory using either the function global free or the macro mFree. Now that we have all of the mechanics up and going, we can get into the genuinely fast stuff. This basic algorithm at its minimum copies data from one buffer to another, but it's designed with a gate between the read and write, so that the YMM register can be modified. As you would expect, the Intel instruction manual could not be described as user-friendly, but if you can get used to the notation, you can find what you need. If you already know the XMM instruction, you generally look for the YMM version that has a leading V, which denotes a 256-bit YMM instruction. In this example, it uses the YMM stack frame with the parameters set manually. The first number, 32, is the important one here. It can be 64 or a larger power of 2, but there is no gain in doing so. The YMM instruction choice is to distinguish between read and write to avoid cache pollution. The non-temporal version avoids writing back through the cache. If you have a use for very high-speed data transfer code, this type of YMM code will get you up into the high end of processing performance. On a test piece on large amounts of memory, the data transfer rate is in the 9 to 10 gigasecond on a legacy Haswell i7. This is why you bother doing the extra work, so you can get the full advantage of high-speed code. That's all I have for you today. Catch you later.